Hello, my name is Sans Emmer. This video is for anybody that's interested in testing the effectiveness of face masks against contagious respiratory illness like COVID. It has been known since the mid-50s that respiratory disease that's contagious is primarily transmitted through respiratory droplets, which are generated through coughing, sneezing, singing, even talking or breathing. You will find these airborne respiratory droplets that contain contaminants such as the COVID virus. With the latest resurgence of COVID, this Delta variant, now there's discussions about the effectiveness of face masks, whether they should be mandated. This discussion, this demonstration here is not meant to be political or to say masks are good or bad. It's really just to show you a simple way for under $100. Any high school teacher, for example, could set up an experiment like this and demonstrate to the students the effectiveness and actually put a number on the effectiveness of different masks. So we're going to be looking at two masks today, the gold standard N95 mask and also equally highly rated surgical masks. And we're going to talk not just about the mask material themselves, but about how important the fit of the mask. So the respiratory droplets that we're interested in, when they talk about airborne transmission of disease, we're talking about droplets that are in the range of 1 micrometer or a micron up to maybe 10 microns or even larger, depending on how it's generated. If you have, well, first, just to get a reference for what a micron is, it's 1/1,000,000th of a meter. If you look at a ruler and look at the tiny little millimeter, we're talking about 1,000th of that. So a human hair, for example, might be 40 micrometers, and we're talking about droplets that are maybe 0.5% of that or up to 1% of a human hair. So airborne transmission requires that droplets are 5 micrometers or less. Once they become about 5 micrometers, they will act, gravity will influence them and they will travel a certain distance, then drop out. I'm sure you've heard this and seen videos where they show these particles and how far they go. But the interesting thing about the droplets is they're not static, they change over time. So even in 100% humidity, these droplets will be evaporating into the air, becoming smaller, even more infectious as far as the concentration of infectious material. So if you have a mask material that's supposed to remove these droplets, you know, we're going to find that out. Okay, to simulate respiratory droplets, we're going to be using this ultrasonic humidifier. And what that does is put out a stream of droplets that are in the size range of respiratory droplets in the micrometer range. And if you observe this flow, you'll see that they're sprayed up and then they're falling. And what that means is the droplets that are greater than 5 microns are under the influence of gravity. They will drop out. However, the vast majority will go into the air and become airborne. That means they're less than 5 microns. And it's kind of an indirect humidification. Like when you put droplets in the air, you're not changing the humidity until they actually evaporate and become a gaseous phase. So, but we're using it before it changes the humidity. We're actually going to detect the presence of these droplets in a very sensitive way, not just by visualizing. This is going full blast. An interesting thing you can do is to, instead of water, you can put tonic water, quinine. The quinine has a very astringent taste, and you can actually, if you take a mask like a surgical mask and you put it over here, you can see that the stream is going through. Now, this isn't a valid test. You're never going to have that kind of concentration of COVID coming at you unless somebody sneezes right in your face. But just the immediate thing is you see that this stream will pass through to some degree. If you put the mask on and put your face in that, you will immediately taste that quinine, meaning that either it's coming around or it's coming through to some degree, which is unknown. You can't put a number on it in this manner. When you put an N95 mask and you make sure it's a good seal, you will still taste it, but it's less. So you could conclude that the N95 is probably better than the surgical mask just based on that very simple experiment. Another cool thing about quinine is it fluoresces. So if you did this in the dark and you had one of those little ultraviolet flashlights, this will fluoresce and you'll be able to see it much better, and you could illustrate it going through a mask or not. But we have a much more sensitive way to detect very tiny concentrations of these particles. To measure the concentration of these simulated respiratory droplets in the air, we're going to be using a very sensitive instrument. It's called an air quality sensor, which uses laser diffraction. It has various sensors at different angles so it can tell when the light is scattered. So not only can it tell the number of particles in the air, but what size these particles are. Very sensitive, very accurate. I'm going to flip the camera so you can see a close-up of what these numbers are. So now I'm zoomed in on this air quality sensor, and what you see are three different scales. This is the default mode. You have particle size on average 2.5 micrometers. We're looking at 50 micrograms per cubic meter in the room air. And then similarly, we have 1 micron diameter particles, 26, and then we have PM10, the larger particles, the 10 micrometer particles. And then over here, temperature, relative humidity, and then what this air quality index. Now you see it says moderate. The interesting thing is that this room quality is normally very good. However, because I ran that ultrasonic humidifier very briefly, and that was like 15 minutes ago, that the air is still contaminated with these tiny droplets that are in the process of evaporating into the air. So just to demonstrate the sensitivity. The scale that I'm going to be using for the experiments, you can push a button here and flip. Now you're actually seeing the particle number of different sizes. So the top scale is the smallest particle, then it goes down to the largest particle. So where it says 0, there's 0 particles that are greater than 10 micrometers, and on up to over 5,000 particles of 0.3 micrometers or greater. So those are the numbers we'll be looking at during the experiment. The flow of artificially contaminated air will be directed through this clear plastic tubing of about 3 inches diameter. About 8 inches from the input end of the clear plastic tubing, I've inserted an air quality sensor which uses laser scattering to measure the number of particles of various sizes ranging from 0.3 microns to greater than 10 microns. So very appropriate for detecting the simulated respiratory droplets. Further down the tube is an insertion into a slightly larger clear plastic tube where I have a rubber gasket which creates a perfect seal, and is upon this gasket which the face masks will be mounted so that we can measure air that is purely directed through the mask, not around it. Further down the line, we have a second identical air quality sensor so that now we can detect the contaminants that are outside the mask and compare them to what actually goes through the mask. And finally, to create the airflow, we've mounted a centrifugal fan that has a flow rate that approximates the maximum human breathing rate. So this is also a very tight seal, so no air can escape around it. The only air that is exiting that fan is being pulled through the tube and thus through the mask. With the fan now running, we have the ultrasonic humidifier located about 3 feet from the input of the apparatus. And we're going to give it about a 5-second blast, which will simulate, for example, somebody sneezing in a room and contaminating the air. I'm now zoomed in on the input sensor. There is no mask in place, so we just got free flow of air through the tube from one sensor to the next. And I am going to turn on the ultrasonic humidifier for a few seconds right now. And now it's back off, and you can see these numbers essentially skyrocketing. Similarly, your other sensors doing the same thing. So the sensors perform virtually identically, which is what you want, and both with extreme sensitivity to these particles of interest. Now I've inserted a 3M N95 face mask. This is considered to be the gold standard of face mask. It is qualified to remove 95% of any particulate matter that is 0.3 microns or greater. Looking at the input, the air is fairly clean. This is with no mist turned on, no contaminants. It's just normal room air. We have 936 particles that are 0.3 microns or greater, and we have 236, 0.5, and then they drop down pretty significantly for larger particles. But we're going to now look at the other side of the mask, which is supposed to be pure. Now we see that indeed the air is much cleaner. We have 144 particles that are 0.3, 44 that are 0.5, and then much lower as you go further down. But these numbers are not what you would expect. They're not as clean as you would expect. We're seeing about 15% of the small particles are passing through the filter. So it is in conflict from what is reported by the manufacturer. Now what we're going to do is add an insult to the outside of the mask. And I'm going to do this with, this is Odor Eaters. It is a foot powder. It's a very fine powder. I'm going to put some into my hand and just blow a cloud near the input. So it will come in, and we're going to look at both the input and the output. But right now we're focused on the clean side of the mask. The numbers have not dramatically risen. This is coming in. These numbers have risen. So we have 1581, 417. So clearly it's detecting the cornstarch cloud, which is not even visible at this point. It's a very dilute cloud. And now it's dropping back to its clean values. But the mask did a very good job of filtering that. It would be hard to say that any of the cornstarch has passed through that mask. So now what we're going to do is to give it a blast from the ultrasonic humidifier and see whether we can detect any increase on the clean side of the mask. So I'm going to turn it on for about 5 seconds, turn it back off. Now you see the dramatic rise. So our simulated respiratory droplets are passing through the mask at a very high rate, Even particles greater than 10 microns are passing through. Those numbers went from 0 to 30. And this is just with a short couple second blast, not even directly into the input. It's still 3 feet away. And if you look at now the input, the numbers are higher, much higher. So the way I would take data for this is to, as the contamination becomes dilute over time, just periodically I would sample this data and look at the input versus the output, and then look at the ratio of those two. This is going back to the clean side of the mask. So right now I've got about 1,200 particles that are greater than 0.3 microns. That's versus 2,000 at the input. So about 50% of these small particles, these respiratory droplets, are passing right through the filter. And even particles as large as greater than 2.5. Right now we have 6 on the clean side and 14 on the dirty side. So now we've taken a surgical mask like this one and inserted it in the pathway over the gasket. Again, it's a perfect seal. All airflow must go through the mask, not around it. This is what's considered a good mask. It's supposed to eliminate or remove greater than 95% of particulate matter. It's not your gold standard, but it's still highly rated. What we're going to do now is look at the clean side, and we're going to zoom in so you can read the numbers. And this is in fair agreement with the input. So what we're going to do is give it another 5-second blast from the ultrasonic humidifier, and we're going to watch what happens. Okay, now it's back off. Now they're starting to climb. So right now the input is reading 33 and the clean side is reading practically 30. So it's almost as if the particles, even the larger respiratory particles, are passing right through the mask. At this point, as the numbers diminish, we've got 12 on the input, 13 on the output for the 10 micron particles. The 0.3 micron and greater is 3,500 versus 4,000 at the input. So you would have to conclude that the vast majority of particles in the respiratory droplet range are passing through this surgical mask with a perfect seal. So I just want to talk for a minute about how these masks are measured. So what they do is they're virtually all tested by the same type of machine, which starts with a saline solution, a 2% solution of salt water, and that is agitated somehow to create an aerosol. That aerosol then goes through a chamber, which is subsequently mixed with clean air, and then it is put through a heating stage, so that the whole point is that the salt will crystallize in these droplets, and the droplets dry out to a hard salt pellet. That pellet is then impinged upon the mask, and the amount of salt that lands on the mask is then compared to the amount of salt that passes through the mask. And that's how they get these numbers that say they're greater than or equal to 95% removal. That's different from a physics standpoint than a respiratory droplet, which is liquid with some salt dissolved in it. So now we're talking about a deformable particle, a particle that can possibly break up, a particle that is dynamic over time. It is, even in 100% humidity, these small droplets will evaporate and become smaller and smaller, thus more likely to pass through a mask. But the big question is, if you have a deformable water-based particle, what happens when it hits that mask mesh network? Does it break up? Does it deform and pass through? A lot of these masks have hydrophobic layers, meaning the liquid will not stick to it. So is it like a pinball machine just allowing these droplets to pass through? It's really not known, and it's not really measured when they're putting a rating on these masks. Another thing I'd like to discuss is the fit of the mask. It's probably even more important than how good the mask actually is how well it fits against your face. And you see people all the time adjusting their masks. You see spaces, around the cheeks. You see spaces under the chin. You see air spaces up, especially between, along the sides of the nose. I don't think people appreciate that it's a problem, because the masks, the better the mask is, the more resistance there is to airflow. So, if it's hard to breathe through a mask, what that means is the air is going to want to take the easiest path and want to go right around that mask in these openings. So to test that, I took, again, the gold standard mask. This is a 3M N95 mask, and I took a razor blade and cut little 1/4-inch slits in 2 spots, and then I inserted, I'll zoom in here, I inserted drinking straws. So what we have is a surface area that is now open to the airflow that amounts to about 1% of the total surface area of my 3-inch tube that the air is passing through the mask. So now I'm going to mount this mask with the designed leakiness into the apparatus, and we'll see what kind of contamination goes through it. So now I have the slightly leaky N95 mask in position, and we're looking at the clean side of the mask, and I will turn the ultrasonic humidifier on for 5 seconds. Now it's back off, and you see almost immediately the numbers skyrocket. So this is vastly worse than the mask without the leaks. And again, this just points out that here you have a mask that's 95% or 99% sealed, and yet the higher airflow through these designed leaks are allowing contaminants to come in at a very high rate. So I'll just talk for a second about how I actually took some data to do these experiments. it's not just like I'm looking at these numbers and seeing that they're going crazy and you get all excited, oh my God. What I did was I would look at the data at both devices at the same time. I'd look at the input, then the output. And I would do this after the initial burst. So you have a high concentration coming in and you have this alarming rise in the numbers. And then you turn your sources off. And now you're going to watch as the concentration diminishes. So these numbers, both before the mask and after the mask, are going to be gradually dropping and become much more stable, not this erratic jumping up and down. So then you can observe over time as the concentration becomes less and less. So maybe over a period of 10 minutes or longer, you can see these numbers and look at the ratio. And also what I did to get a more accurate amount was I subtracted out the original baseline. So whatever the level of contaminants in the room, whether it's from pollen, some other allergen, dust, whatever it is, it's some low number, but you're going to subtract that. So inside the mask, you've got much cleaner. You're going to subtract a smaller number from whatever number you're reading with the contaminant. And then on the outside, you're going to subtract that larger number. And then, so your ratio is then purely dependent on the contaminant of interest, which is the simulated respiratory droplets. So if you look at these numbers, and what you find is after that initial burst, it becomes kind of independent of the concentration of the contaminant. So whether it's a moderate contaminant going down to low, you still see about the same ratio, which is good. It means the mask isn't saturated or somehow in a situation that's unrealistic. The other thing of interest was there's not a huge difference over this particle range from 0.3 microns or greater all the way up to 10. You still see this similar ratio of, how well the mask is doing. And it seems like you would expect it to be way worse at the smaller particle, but it actually is not so great for these 10 microns or greater. So if I average them out, what I concluded was for something like the gold standard N95, it's removing about 85% of the particles that are in the air, and that's with an absolutely perfect seal. 85%. So the claim that they make is that it removes 95% of particulate matter that is 0.3 micrometers or greater. But again, that's a solid, they're actually impinging grains of salt. So you have to take that data with a grain of salt. So you might immediately say, well, 85%, that's not bad. They say 95%, it's 85%. But when you think about it, for every 100 infectious particles that are in the air, 15 are coming through, as opposed to what should be 5 or less. So that's actually 3 times worse as far as the effectiveness against something like COVID. If you then move on to the surgical mask, where these are also supposedly will remove 95% or more of particles, you find that this is much worse. Even with a perfect seal, it's much worse. This will allow about 45% of particles, respiratory droplets coming through. So vastly worse, and that's with a perfect seal. If you take the N95 mask that had the designed tiny holes in it, so now you have 1% leakage, that immediately, just that small amount of leakage brings it to the same level as the not so great surgical mask. So just showing how important that seal is, and it's probably impossible to get that kind of perfect seal with, definitely not with this, but even with this, it's hard to get a great seal, or else you're going to be lowering your effectiveness of the mask. The final thing, cloth masks, these homemade, I don't care if it's 1 layer, if it's 2 layers, it's not effective. That stream from the humidifier will go right through it. You will taste that quinine, very strong. the instruments will go crazy with something like even 2 layers of a thick t-shirt material. So I'm just not even going to address that, but I just would say get a good mask if you're going to wear a mask.